Hmm? Stage is yours.
I think it's, hi, okay, thank you. Hi, welcome everybody. Um, First and foremost, I have to give credit to Jan. We're doing this project together, and I'm merely, I guess, his PR person and poking him from time to time to the features I need for contracts. Um, when we say beyond Wasm, let's tackle the obvious question first, like, why not Wasm? And if you like a bit like deeper into the things, you would know that not everything is as rosy as you might think. So there are always like discussions between engineers. Maybe there's another way. Um, maybe there's another way than use Wasm for smart contracts. And the most obvious, like the most pressing issue is like, yeah, Wasm is really hard to compile to a native computer. So when we run a smart contract, we kind of have to run those instructions. And usually we do it with interpretation, which is really, really slow. But the gold standard is compilation. So we take a smart contract program, take the WebAssembly, compile it to x86 or ARM or anything real, and then we run it. And we like, ever since I started 3.5 years, it was always like, okay, we will have compilation one day, we will have it one day, but it never happened because it's just hard to do it with WebAssembly. So a while back, like I was thinking like maybe there's a better way, and then I just thought like, okay, there's this guy Jan we have at our company. He's very good at cross compilation and stuff. So I talked to him. We were talking a bit, and then we landed on maybe we can do something new. But let's take a step back, like because like wait a second, we have Wasm time. We use it for all the parrot chains, and it seems to work fine, right? So why don't we use that for a smart contract and just use Wasm time? We can be as fast as the runtime itself. That would be nice, right? But it doesn't really work because when you take Wasm time and try to compile a contract with it, you never know if it will finish. I mean, you will never know if it will finish the compilation. And if you're up in the stack where contracts are, you have to know all the weights. You can't do like those little tricks that we can do with the runtimes. You have to know if I put in this Wasm blob, you will have to know if it finished, and we can't do that with Wasm time. And Wasm time is also slow to compile. And that's bad for us because when we run contracts, we can't cache the compilation. I mean, we kind of could, but it makes things more complicated. It's a topic for itself. Let's just assume for a second that we can't cache the artifacts like of the contracts compilation. So what that means is every time we run a contract, we have to compile the contract, then run the contract. That makes the compilation itself part of the block space or core time. Or how you want to call it. So we have to do fast compilation. And because it's like so hard with Wasm, like what we've been doing so far is just interpreting it with Wasm. It's our in-house interpreter. Like, okay, like very important to understand is like why is it so hard to compile? The thing is, if you look at WebAssembly, it's a stack machine, and all the existing computers are register machines. And the only difference you need to understand is like, how do those computers pass variables between functions, like the arguments between functions? A stack machine will put it on a stack, call into the function will take off the stack. And if you want to transform WebAssembly to a register machine, which are all real computers are, you have to kind of like all the things which are on the stack in which registers do we put them. That's really hard, and that makes compilation really, really slow. So you always have this trade-off, like how much time do we spend on compiling this program? So you always have to make a trade-off. And if you never know how to make this trade-off, because it all depends on the program. Will it run for a long time? Like how much time can we spend on compilation? And the other reason why it's hard to compile is that WebAssembly is not really like a low-level instruction set. It's more like a programming language. If you look at it, it has blocks, it has if, it has else, so all the things you would recognize from a C program, which also makes it hard to compile, because if you want to transform it to a real computer, you don't have those things. You just have jumps. You just jump between codes, and this also takes processing time. What are other reasons why WebAssembly doesn't work that well for us? First, the stack in WebAssembly is indeterministic. That means if you run a WebAssembly virtual machine, it's not defined how many items you can push on the stack. It's completely up to the implementation when it will overflow, which is kind of bad if you run a blockchain, because you always have to know that everywhere you run it, it has to be the same. So we have to inject code to make sure it's absolutely the same anywhere, which also slows down everything. And it's also like, Wasm is not really tailored towards blockchain, so all the companies working on it, they're like in the cloud business and stuff. And like what demonstrates that pretty well is, like every half a year, someone from Parity tries to open a PR with Wasm time to make like this Wasm parser component being able in no STD, and will always be shut down because we don't do that here. And WebAssembly is also moving target, which means we have this little WebAssembly MVP, which we target with our blockchains, and it's expanding. So they always like add new stuff to it, which is kind of bad for us. Okay, so we looked at all those things, why it's kind of hard to use WebAssembly, and then you think like, does compilation have to be that hard? Maybe there's another way. So the idea is like, wait, if real computers are register machines and all the virtual machines are stack machines, why don't we use like a real computer as our virtual machine? And this is what we went with. Like, let's just like look at all the real instruction set we have. Like we have x86, we have ARM. Why don't we use those? It's more similar to a real computer. It's less work for compilation. And finally, we landed on RISC-V, mainly because it's just the most simple computer of all. And I think a good proxy for that simplicity is if you just look at the number of instructions. So like on the right side, we just have like 150 instructions, which is just like a basic Intel computer, like from the 1990s or something. I mean, right now they're like over 600 by now, but I just included relevant instructions, so no floating point, just the things which are relevant to make the comparison fair. So I would say it's a fair comparison. If you would have an Intel virtual machine, you would have to implement all those instructions. And even ARM is supposedly simple, but like with our RISC-V, so this RV32EM is a target name we're using, we can still do better. So now, okay, we use RISC-V for a virtual machine, but like, how does it help us? And the main reason is we avoid this pesky register allocation. We don't have to think about, okay, we have those stack, all those registers, and we kind of like need to decide like where do they go on the host machine. So we avoid this completely. But there's one problem, that if you look at Intel x86 64, it has only 16 registers, and RISC-V has too many. So we basically back to square one. We still have this problem. We have too many registers. We have to put them in, like we still have to make an allocation. But there's a way. So while looking at that, we saw like, okay, there's like a new variant of RISC-V, which is called RISC-V embedded, and there's an open PR against Rust where they add this target, and it essentially just reduces the register set to 16, which would allow us, if we compile our contracts or our runtime to this target, that we can just have a one-to-one mapping. So the compiler would be that simple. It would just take, it would be just a one-to-one mapping from the registers of RISC-V to x86. And this is where this Polka VM comes in. This is the name Jan gave it, which is essentially a RISC-V virtual machine. I mean, it's not really RISC-V. He made some modifications to the instruction set, but it's slight modifications to make it working better for a use case. The logic is, if we do something custom, we can go fully custom and just tailor it so it's perfect for a use case. So for now, it's only 32-bit support, but 64-bit support will be coming. We're not using ELF as a container. So when you compile a program with Rust, you will get it in an ELF container. We use our own container, so we have some post-processing. And the compilation will be linear. So you will always know it will hold, it will compile in linear time. So if you give, it will be proportional to the amount of code you compile. And we will see this later. I have some numbers that it's already faster than Wasm, which is like the fastest linear compiler which exists for WebAssembly, which is like years in development and a lot of lines of code. So how do we compile a contract to Rust or to Polka VM? How does the execution work? So we start with some Rust code. It could be a contract. It could be a runtime. We take this code, put it into Rust-C or cargo build. Then we get an ELF binary. Up until this point, it's all completely standard. And then we have this program which is called Polka VM Linker, which takes the ELF file, does some processing, transforms it to what's called Polka VM blob. So I guess we're still looking for names for it. And this all happens on the developer's computer. And then this Polka VM blob will be uploaded, for example, to pallet-contracts, and then the compilation will happen to the target instruction set, which will be Intel, x86, or if you run an Apple computer, it will be ARM. But right now, we don't support ARM yet. OK, let's look at some numbers. So this is so what we have to take into account is like the compilation time and the execution time. Like the function of like if you run a contract, how much gas fees it will incur is like we have to compile the contract and then we have to run the contract. So and you can make trade-offs here. Like, do we just spend a little bit of execution time? This would be Wasm, basically a little bit of compilation. Wasm doesn't really do compilation because it's an interpreter. So it has just under a millisecond of compilation time and then immediately just runs the code. And we can see that Polka VM already is strictly better than Wasm. It takes like a fraction of the compilation time, but delivering the same performance. So it's just strictly better. There's no reason why to use Wasm, basically. And you have to keep in mind, this is like version 0.1. So there's no optimization in there whatsoever. It's just like coded it down and very naively. But what you have to keep in mind is like it's like totally you never know how important is compilation time, because when you compile, like when you run a contract, you compile the whole contract, but then you run it for a while, and the longer you run it, the more important is the execution time. So this is why this whole endeavor was started, because we can't make this trade-off. We need something which is better, which compiles faster, but doesn't trade it for execution time, which will always be the case if you use a stack machine. Okay, what does it mean for pallet-contracts? So we have this Polka VM now. we already started porting pallet contracts, so there is code existing, so it kind of works end to end. But the goal here is that we support both bytecodes. So you upload a contract, doesn't matter if it's WebAssembly or RISC-V, and they just can call each other, so it's completely seamless for the developer. You don't even have to know in which bytecode the contract is formulated. The migration will also be easy. You don't have to do any changes to the contract itself. You just upgrade to a new ink version and recompile it, and that's all you have to do. And it's transparent for the client tooling. So if you have some front end or anything, you will still upload the same .contract file. It will just, in this code entry, it will just contain a RISC-V binary, but tools shouldn't peek into this anyway. So for them, it's opaque. Okay, what are the next steps for pallet contracts? So we have this proof of concept, which exists. But the next big step we have to do, we have to standardize this host function. Because when you want to run RISC-V contracts, we need a new host function. And eventually, it has to go into Polkadot too. Because if you want to run it on a parachain, it has to be validated on Polkadot. And so this host function has to be there. And it's kind of like a big host function with a big attack surface, so we have to make sure that we don't do any mistakes here, that we standardize this properly, so other clients have a chance to implement it too. Otherwise, you would end up in a situation where it would run on a Substrate client, but not on alternative implementations, and then it would never make its way into Polkadot. Okay, what about runtime? So the case for contract is pretty clear-cut. So we just basically need this because we want to compile faster. But for the runtime, it doesn't really matter because we can cache the contract. We can cache the compiled runtime. So we don't really have to compile fast, but there's still upsides. So we can get rid of this pre-checking. Anybody working on this will know what it means, and it's like annoying. We don't have to deal with the indeterministic stack. But so essentially, we will simplify the whole process. But right now, we can't really switch because the performance of the RISC-V VM is still 50% slower than Wasm time. So the goal is we have to demonstrate then we can get the same runtime performance there, and then we might be able to switch, but it's not as clear-cut. Okay, what's next for Polka VM? So it's version 0.1 now. What we really want to get in before we deploy it for contract is 64-bit support, because 32-bit support would be a regression from WebAssembly, because in WebAssembly we have 64-bit integers, like 64-bit registers, and we don't have them in our current target, so we want to implement that first. Of course, we need gas metering for contracts. It's also not implemented yet. And right now, it only runs on Linux. Like the recompiler only works on Linux. On all other platforms, it runs in the interpreter, which is kind of okay because almost all validators run Linux. But yeah, we don't want to add another impediment to, let's say, innovation on the operating system level. Okay, how to get involved? I think at this stage, you can just check out this Polka VM repository. It's under Jan's handle, and just try to play around with it and report bugs, and maybe contribute like some improvements for your operating system or architecture of choice, because right now it's Linux x86 only. And of course, there's a Polkadot forum thread where you can weigh in if you want to. Okay, thank you for coming. I think we take questions now, right? Thank you.
Now we have 5 minutes more and would be happy if somebody has a question. So please raise your hand. I will come to you. And Alex, you just stand there.
Mm-hmm.
Nice.
I stand here. Okay.
Hello. Quick name and then question.
Hi. I'm wondering if there is a plan to use Polka VM or RISC-V as an alternative for the validation function of Polkadot. So like to have parachains compiled, parachains runtimes compiled to RISC-V instead of Wasm.
Yeah. Yeah, I think that's what I meant when like for the runtime. So like yeah, I mean the terminology is a bit difficult, but yeah, when I say like we might want to use it for the runtime, I also meant like for the parachain validation function, and we might want to do that, but right now we don't know because the performance is not there yet. So the execution performance is half of the performance of Wasm time, and we don't want to regress the execution performance.
Okay, thanks.
Thank you very much. Another question? Please raise your hands. No. Quick name and then the question.
Yeah, thanks. It's rather not a question, but a comment. Yeah, as I know, Moonbeam, for example, they also not using Wasm, so obviously they use EVM, and that doesn't stop them to be validated by relay chain. So as far as I know, they have their own host APIs for EVM, and they use some kind of off-chain workers for parachain. So relay chain even not executing these host APIs, even though they exist for EVM. So in theory, I think, yeah, if there is some parachain that uses this RISC-V host API that you introduced, I think there are, yeah, you might maybe check out how Moonbeam is doing that, so that, yes, the code is still validated by relay chain.
Yeah, okay. Yeah, thank you for the comment. The reason why it works for Moonbeam is because Moonbeam is not using a recompiler. They're using an interpreter. So they just compile the interpreter into the runtime itself, which means they don't need a host function. But if you have a recompiler, you can't do that within the runtime, because by principle, it needs to happen at least partly inside the client, because if you recompile something, it's platform dependent. So as soon as you go from interpretation to compilation, you have to have some client support for it. And Moonbeam is just interpreted, so they don't have to have a host function.
Cool. Thank you very much. And now, if someone else has a question, just go directly to Alexander, hit him up, and I think you can answer them then there in person.
Okay.
So
Thank you. Thank you for coming.
Thanks.